Now in this lecture we'll find out the length of chord CB. In the drawing we have a semicircle. We know that the center of this semicircle is at this point O. Inside the semicircle we have a square DEFO, this square, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord called CB. So first of all, because of the fact that DEFO is a square, we know that all the angles inside the square are right angles, therefore those 4 angles, they are all right angles if each of them is equal to 90 degrees. So I'll write it down, this angle equals to 90 degrees. This angle it is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle equals to 90 degrees. And we know that the area of this square is equal to 5 square units. So we can write down that the area of square DEFO is equal to 5 square units. Here, the squared brackets is the sign for the area. Here's the area of square DEFO. The area of square DEFO equals to 5 square units. And we know that the area of any square, if this is a square, then the area of this square equals to the length of the square times the width. This is the area of this square. The length times the width, but because of the fact that the length equals to the width, we know that all the sides of the square are equal to each other. Therefore, the area of this square will be the length of one side times the length of the other side. That is the area of the square. And the area of the square is equal to the length of one side squared. So actually, we know that the area of square DEFO is equal to 5 square units. So we can substitute the area by 5, and it is equal to the side of the square squared. Here we'll take a root out of this equation and we get that the length of one side of square DEFO is equal to the square root of 5 units. That is to say, all the sides of square DEFO are equal to square root of 5 units in their length. In the next step, we join points D and O together by a straight line. By joining points D and O, we created triangle DOF. Triangle DOF is a right triangle because of the fact that this angle equals to 90 degrees. Okay, so the green triangle DOF is a right triangle. So I'll copy the triangle to a new page and we'll implement the Pythagoras theorem on this green right triangle DFO. This is the right triangle DFO with the coordinates from the original drawing. DF equals to FO equals to the square root of 5 units. Both of them are the size of the square. So we can implement the Pythagoras theorem on this right triangle, triangle DFO. So here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle DFO is DO, therefore the square of the hypotenuse is DO square. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to DF square plus FO square. So DO square equals to df square, df equals to the square root of 5, therefore df square equals to the square root of 5 square, plus fo, fo is also equals to the square root of 5, therefore fo square equals to the square root of 5 square. So do square, this is the square of the hypotenuse, equals to square root of 5 square is of course 5, plus square root of 5 square is 5. So if I know that do square is equal to 5 plus 5, that is 10. We will take a root out of this equation and we get that the length of the hypotenuse DO is equal to the square root of 10 units. Here, DO equals to the square root of 10 units. You can write in the original drawing that DO equals to the square root of 10 units. That is the length of the hypotenuse of the green right triangle. But DO is not only the hypotenuse of the green triangle, but it is also the radius of this semicircle. Why? Because of the fact that it starts from point O, that is the center of the semicircle, and ends at point D, that is a point on the semicircle itself. This is exactly the definition of a radius. So we can write down that DO is the radius of the semicircle. We know that it is equal to square root of 10 units. So we know that the radius of the semicircle equals to the square root of 10 units. What is line segment OB? Line segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, OA, line segment OA starts from point O, that is the center of the semicircle, and ends at point A, that is the point of the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. In the next step, I will present to you a new rule, rule number 1, and we'll implement rule number 1 in our drawing. Okay. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. We'll explain what is the meaning of this rule, rule number 1. So actually, if we have here straight line AB, AB is the straight line. If we choose any point on the straight line AB, for example, we'll choose this point, we define this point as point K, and we have side KL, this is side KL, on the straight line AB. So if we focus on the upper side of the straight line AB at point K, which angles we have at the upper side of AB at point K, we have this angle LKA, plus this angle LKB. And according to rule number 1, the sum of those two angles, that is to say, angle LKA plus angle LKB must be equal to 180 degrees. That is to say, the sum of the angles on the upper side of the straight line AB at point K must be equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees. The same thing is true about the lower side of AB. This is the lower side of the straight line AB, and therefore, according to rule number 1, the sum of the angles in the lower side of the straight line AB at point K, that is to say, this angle must be also equal to 180 degrees. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing we have the semicircle, this is the semicircle, according to what is given us in the question. And here, AB, it is the diameter of the semicircle. So AB is the diameter of the semicircle, it is absolutely a straight line. Okay, so if we focus on the upper side of the straight line AB at point O, on the upper side of AB at point O, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees. Plus the missing angle that is actually angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. I'll repeat again. In the upper side of the straight line AB at point O, the sum of the angles must be equal to 180 degrees. That is to say, this angle that is equal to 90 degrees plus the missing angle that is actually angle EOB, in total they must be equal to 180 degrees. We'll subtract 90 degrees from this equation, and we'll get that the missing angle EOB equals to 180 degrees minus 90 degrees, it is equal to 90 degrees. So if I know that angle EOB, it is a right angle. This angle, it is a right angle. And because of the fact that angle EOB is a right angle, then you can conclude from it that triangle EOB, the peak triangle EOB, must be a right triangle. Therefore, we can implement the Pythagoras theorem on the right triangle, triangle EOB. Okay, so I will copy the right triangle EOB in a new page and we will implement here this triangle, the Pythagoras theorem. This is the right triangle EOB. Let's take copy it from the original drawing. This is the right pink triangle EOB. This right triangle. Now we will implement the Pythagoras theorem on this right triangle. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. The hypotenuse in this right triangle EOB is EB, therefore the square of the hypotenuse is EB square. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO square plus OB square. Okay? So EB squared, that is the square of the hypotenuse, must be equal to EO square. EO equals to the square root of 5 units, therefore EO square equals to the square root of 5 square plus EB square, EB plus OB square. OB square, OB equals to the square root of 10, therefore OB square equals to the square root of 10 squared. So in conclusion, we found out that EB squared, the square of the hypotenuse, equals to square root of 5 square is of course 5 plus square root of 10 square is 10. That is to say EB square equals to 5 plus 10, that is 15. We'll take a root out of this equation and we'll get that EB equals to the square root of 15 units. EB equals to the square root of 15 units. The hypotenuse EB equals to the square root of 15 units. You can write in the original drawing that 97 EB equals to the square root of 15 units. Our mission is to find out the length of chord CB, this chord. We have already found out that EB equals to the square root of 15 units, therefore the only thing that is left to find in order to find out the length of CB, is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction, we will complete the semicircle to a circle in the first step. So in the first step, I have completed the semicircle to a circle. In the next step, we'll extend line segment OE on both sides, in the upper side and in the lower side. The first step, we'll extend line segment OE by a straight line towards the upper side of the circle until it touches the circle, and we'll define the touching point of the extended line segment OE with the circle as point M. In the next step, we will extend line segment EO towards the lower side of the circle until it touches the circle. And we'll define the touching point of the extended line segment EO and the circle as point N. Okay, so what is the definition of line segment ON? Line segment ON starts from point O, that is the center of the circle, and ends at point N, that is the point of the circle itself. This is exactly the definition of a radius. We know that the radius of the circle and the semicircle is equal to the square root of 10 units. Therefore, ON equals to the square root of 10 units. Okay? And what is the length of line segment EN? It is very easy to see from the drawing that EN equals to EO plus ON. Again, EO plus ON equals to EN. It is EO plus ON. So EN equals to EO, that is equal to the square root of 5 units, plus ON, that is square root of 10 units. In conclusion, we found out that the length of line segment EN equals to the square root of 10 units plus square root of 5 units. Likewise, what is the length of line segment ME? The length of line segment ME, from the drawing it is very easy to see that ME equals to MO minus EO. I'll repeat again. ME equals to MO minus EO. So ME equals to MO. O is the center of the circle. M is the point of the circle itself. This is exactly the definition of a radius. Therefore, MO is the radius of this circle, that is equal to the square root of 10 units, minus EO, that is equal to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. ON equals to the square root of 10 units, and here EB equals to the square root of 15 units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, that will be actually rule number 2. Rule number 2 is true in any circle, so I'll write it down. In any circle, so here, the circle that I will draw could be any circle. If chord AB, this is chord AB inside the circle, intersects with chord CD, this is chord CD, chord CD intersects with chord AB at this point. This is the intersection point. We define the intersection point as point O. So if chord AB intersects with chord CB at point O, I'll write it down. If chord AB intersects with chord CD, chord AB intersects with chord CD, and the intersection point between the two chords is defined as point O. Then the following equation is true. AO times OB equals to CO. This is actually called CD. So AO times OB equals to CO times OD. Repeat again, according to rule number 2, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule number 2 in our drawing. Well, because in our drawing we have chord MN that intersects with chord CB at point E. Okay, so I'll copy the two chords that intersect with each other in a new page, and we'll implement rule number 2 in our drawing. So here we have now a specific circle. We have two chords that intersect with each other. You can see from the original drawing that chord MN passes through the center of the circle, that is to say from point O. Okay, so this is chord MN. That intersects with chord CB. This is chord CB. In the intersection point of the two chords occurs at point E. We've already found out that ME equals to the square root of 10 minus square root of 5. We've already found out that EN equals to the square root of 10 plus square root of 5, and we've already found out that EB equals to the square root of 15. CE is the missing line segment. So here, according to rule number 2, so I write it down first of all that in our original drawing we have chord MN. It's called MN that intersects with chord CB. At point E. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. I'll repeat again, because of the fact that chord MN intersects with chord CB at point E, therefore ME times EN equals to CE times CB according to rule number 2. So we know that ME equals to the square root of 10 minus square root of 5, so we'll substitute ME by square root of 10 times minus square root of 5. We know that EN equals to the square root of 10 plus square root of 5, so we substitute EN by square root of 10 plus square root of 5, plus, and it is equal to CE. CE is the missing line segment, so we leave it as it is, times EB. EB equals to the square root of 15, so we substitute EB by square root of 15. Here we have square root of 10 minus square root of 5 times square root of 10 plus square root of 5, according to the rule that A times B equals to B times A. We can change the order here and write down that square root of 5 plus square root of 10 times square root of 5 times square root of 10 minus square root of 5 equals to CE times square root of 15. Here, square root of 15 plus square root of 5 times square root of 10 minus square root of 5. You can find the value of this expression by using the trigonometric identity, the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to the square root of 10, I write it down. A equals to the square root of 10, and B equals to the square root of 5. And according to this algebraic identity, A plus B times A minus B equals to A squared minus B squared. So our expression equals to A squared minus B squared. If A equals to the square root of 10, then A squared equals to 10, of course. Here B equals to the square root of 5, therefore B squared equals to 5. So it is A squared minus B squared, that is to say 10 minus 5. And according to rule number 2, this expression equals to CE times square root of 15. Ten minus 5 is 5, so 5 equals to CE times square root of 15. Here we will divide this equation by square root of 15, and we get that CE, the missing line segment, equals to 5 over square root of 15. So we actually found out that the missing line segment CE equals to 5 over square root of 15. So write down here that C equals to 5 over square root of 15. And what is the length of chord CB, the chord that we are looking for? It actually equals to CE plus EB. So write it down. CB equals to CE plus EB. Repeat again. For the domain, it is very easy to see that CB equals to CE plus EB. That is to say, CB equals to CE. We just right now found out that CE equals to 5 over square root of 15, and we have already found out that EB equals to the square root of 15. So the answer to our question is that the length of chord CB, the chord that we are looking for, is equal to 5 over square root of 15 plus square root of 15. Here we will simplify this expression Why? Because we don't want that in the denominator we have a square root. Therefore, we'll actually multiply square root of 15 by square root of 15, and then we'll divide it by square root of 15. We actually multiply it by 1, so we change nothing. Therefore, it is allowable. In this way, we will have a common factor with this expression. So CB equals to 5 over square root of 15 plus, we will multiply square root of 15 by square root of 15, and then we divide it by square root of 15. So we found out that CB equals to 5 plus square root of 15 times square root of 15, it is equal to 15, of course. So in the numerator we have 5 plus 15, in the denominator we have square root of 15. So in conclusion, we found out that CB equals to, in the numerator we have 5 plus 15, that is 20, over in the denominator we have square root of 15. Here we will multiply this expression by square root of 15, and then we will divide it by square root of 15 in order to eliminate the square root of 15 in the denominator. So CB equals to 20 times square root of 15 over square root of 15 over square root of 15. This is the original expression. We multiply it by square root of 15, and then we divide it by square root of 15. So here CB equals to 20, in the numerator we have 20 times square root of 15 over square root of 15 times square root of 15 is of course 15. Here we will divide both the numerator and the denominator by 5. CB, so 20 over 5 is 4, so in total the numerator we have 4 times square root of 15, and then 15 over 5 is 3. So in conclusion, we found out that the length of the chord that we are looking for, CB, it is either equals to 4 times square root of 15 over 3, or in terms of numbers it is equal to 5.164 units. This is the answer to our question. I'll repeat again. The length of the chord that we are looking for, chord CB, it is equal to either 4 times square root of 15 over 3, or in terms of numbers, the length of chord CB equals to 5.164 units. In the next step, I will summarize the lecture. Okay. So, in the original drawing, we had a semicircle. This semicircle, we know that the center of this semicircle is at this point, point O. Inside this semicircle, we have square DEFO. This is a square. And we know that the area of this square DEFO equals to 5 square units. And our mission is to find out the length of this chord called CB. Okay, so first of all, because of the fact that this is a square, DEFO is a square, therefore all the angles inside any square are right angles. So those 4 angles that are inside square DEFO are all right angles. Each of them is equal to 90 degrees. And we know that the area of any square is equal to the length of the square times the width of the square. But because of the fact that all the sides of a square are equal to each other, it means that the length equals to the width. So the area of this square will be equal to one side times the other side. They are the same in their lengths, so it is side times side. That is to say, the area of this square equals to the side squared. And we know that the area of our square is equal to 5 square units, so we can substitute the area by 5, and we know that the area equals to the side, or the length of one side of the square squared. Okay, so 5 equals to the side squared of our square. We took a root out of this equation, and we found out that the length of one side of our square, DEFO, equals to the square root of 5 units. So here, all the sides of this square are equal to square root of 5 units, each of them. Okay, so then we joined points D and O together by a straight line. By joining points D and O by a straight line, we actually created here the green right triangle DOF. Why it is a right triangle? Because of the fact that this is a right angle. So I copied the right triangle DFO, the green triangle, in a new page, and we implemented the Pythagoras theorem on this green right triangle DFO. So this is the right triangle DFO that I copied from the original drawing. We know that DF equals to FO, they are both equal to the square root of 5 units, they are the size of the square. The only missing side is the hypotenuse DO, so we can implement the Pythagoras theorem in order to find out the length of the hypotenuse DO. According to the Pythagoras theorem, here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is the O, therefore the square of the hypotenuse is the O square, and the O square must be equal to dF square plus FO square. So dO square equals to dF square. dF equals to the square root of 5, therefore dF square equals to the square root of 5 square plus FO square. FO equals to the square root of 5, therefore FO square equals to the square root of 5 squared. So in conclusion, we found out that dO square equals to the square root of 5 square plus square root of 5 square. So dO square equals to the square root of 5 squared, that is 5. So it is 5 plus square root of 5 square, that is 5. So in conclusion, we found out that dO square equals to 5 plus 5, that is 10. We took a root out of this equation, and we found out that DO, that is the hypotenuse of this triangle, DOF, is equal to the square root of 10 units. So here, the hypotenuse DO of the green triangle is equal to the square root of 10 units. DO is not only the hypotenuse of the green triangle, but it is also the radius of the semicircle. Why? Because line segment DO starts from point O, that is the center of the semicircle, and ends at point D, that is the point on the semicircle itself. Therefore, this is exactly the definition of a radius. Therefore, DO is the radius of the semicircle, that is equal to the square root of 10 units. That is to say, the radius of the semicircle equals to the square root of 10 units. Okay? And what is the definition of OB? Line segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is the point on the semicircle itself. Therefore, OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, OA, point O is the center of the semicircle, point A is the point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. Then we focused on the, actually I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So AB is a straight line, and if we focus on the upper side of the straight line AB here at point K. According to this rule number 1, the sum of the angles on the upper side of AB at point K must be equal to 180 degrees. That is to say, the sum of those two angles must be equal to 180 degrees. This angle is angle LKB, plus this angle, it is angle LKA. So the sum of those two angles is LKA plus LKB. In total, they must be equal to 180 degrees according to this rule number 1. The same thing is true if you focus on the lower side of the straight line AB here at point K. Here the sum of the angles must be also equal to 180 degrees. So this angle must be also equal to 180 degrees. So we can implement rule number 1 in our drawing. Why? Because in our drawing we have this semicircle. Here AB is the diameter of this semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So AB is a straight line. If you focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees plus the missing angle, that is actually angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. Okay, so you can write down that if you focus on the upper side of AB at point O, the sum of the angles must be equal to 180 degrees. That is to say, we have one angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. Here we subtracted 90 degrees from this equation, and we got that angle EOB, the missing angle, equals to 180 degrees minus 90 degrees, it is 90 degrees. That is to say, here angle EOB, this angle, equals to 90 degrees. So if angle EOB equals to 90 degrees, it means that triangle EOB, the pink triangle, is right angle. So you can implement the Pythagoras theorem on the right pink triangle EOB. So I copied the right triangle EOB in a new page and we implemented the Pythagoras theorem on it. Okay. So this is the right triangle EOB that I copied from the original drawing, the right pink triangle. We know that EO equals to the square root of 5 units. OB is the radius of the semicircle that is equal to the square root of 10 units. The only missing side is side EB. So we can implement the Pythagoras theorem in order to find out the length of the hypotenuse EB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB square. And EB square must be equal to EO square plus OB square, that is the sum of the squares of the perpendiculars. Okay, so EB square equals to EO square plus OB square. So EB square equals to EO square. EO equals to the square root of 5, therefore EO square equals to the square root of 5 square plus OB square. OB equals to the square root of 10, therefore OB square equals to the square root of 10 square. So in conclusion, we found out that EB square equals to the square root of 5 square, that is 5, plus square root of 10 square, that is 10. So in conclusion, we found out that EB square equals to 5 plus 10, that is 15. EB square equals to 15, we took a root out of this equation and found out that EB equals to the square root of 15 units. So here, you can write down that EB, the hypotenuse EB equals to the square root of 15 units, and here also EB equals to the square root of 15 units. We are looking for the length of the chord CB, this chord. We have already found out that the EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. This line segment CE, in order to find out the length of line segment CE, we did the construction. We completed this semicircle to a circle, and then we extended line segment EO on both sides, in the upper side and in the lower side. We extended OE by straight line towards the upper side until it touches the circle at point M. Then we extended EO towards the lower side of the circle until it touches the circle at point N. What is ON? O is the center of the Circle end is the point in the circle itself, therefore ON, it is the radius of the circle that is equal to the square root of 10 units. Okay? And what is the length of EN? From the drawing it is very easy to see that EN equals to EO plus ON. Again, EN equals to EO plus ON. EN equals to EO plus ON. So EN equals to EO, that is square root of 5, plus ON, that is square root of 10 units. In conclusion, found out that here EN equals to the square root of 10 plus square root of 5 units. And what is the length of line segment ME? From the drawing it is very easy to see that the length of line segment ME, here ME, it is equal to MO minus EO. Again, MO minus EO equals to ME. So ME equals to MO minus EO. This is to say ME equals to MO. MO is the radius of the circle, therefore it is equal to the square root of 10 units, minus EO, that is equal to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 minus square root of 5. Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, that is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, point O is the intersection point between the two chords, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 2 in our drawing. Why? Because in our drawing, we have chord MN, this is chord MN, that intersects with chord CB at point E. Point E is the intersection point between the two chords. So I copied the two chords in a new page and implemented them rule number 2 in our drawing. This is chord MN, that intersects with chord CB at point E. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5, EN equals to the square root of 10 plus square root of 5, and EN and EB equals to the square root of 15. The only line segment that is missing is CE. Okay? Again, according to rule number 2, ME times EN equals to CE times EB. So we can substitute ME by square root of 10 minus square root of 5. We can substitute EN by square root of 10 plus square root of 5. C is the missing line segment, so we leave it as it is. We can substitute EB by square root of 15. So in conclusion, we found out that square root of 15, the square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. Here, because of the fact that according to the algebraic rule that A times B equals to B times A, we can change the order of those two expressions. That is to say, instead of writing down that square root of 10 minus square root of 5 times square root of 10 plus square root of 5, we can write down, we can change the order, square root of 10 plus square root of 5 times square root of 10 minus square root of 5. Why? Because A times B equals to B times A. And this is according to rule number 2, it is equal to CE times square root of 15. According to the algebraic identity that A plus B times A minus B equals to A square minus B square, we can use this trigonometric identity in order to find out the value of this expression. In our specific expression, A equals to the square root of 10 and B equals to the square root of 5. And this expression equals to A square minus B square. Okay? Again, in our specific expression, A equals to the square root of 10 units, B equals to the square root of 5 units. And our expression equals to A square minus B square. If A equals to the square root of 10, then A square equals to 10 minus B square. B equals to the square root of 5, therefore B square equals to 5. So minus b squared is minus 5. So in conclusion, we found out that this expression equals to a squared minus b squared, that is to say it is equal to 10 minus 5. So in 10 minus 5, according to rule number 2, it is equal to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. Here we divided this equation by square root of 15 and found out that CE, the missing 9 segment, equals to 5 over square root of 15. Here CE equals to 5 over square root of 15. Here we can write down that the missing 9 segment CE equals to 5 over square root of 15. We are looking for the length of chord CB. And CB, it is very easy to see that CB equals to CE plus EB. Again, CB equals to CE plus EB. Okay, CB equals to CE plus EB. CB equals to CE. CE equals to 5 over square root of 15. And we have already found out that EB equals to square root of 15. So the answer to the question is that the length of this chord called CB, it is equal to 5 over square root of 15 plus square root of 15. Here we simplified this expression in order to eliminate the square root in the denominator. Actually, we multiplied square root of 15 by square root of 15 and then we divided by square root of 15. So we actually multiplied by 1, so we changed nothing. Therefore, it is allowable. In this way, we created a common factor with this expression. So it is CB equals to 5 over square root of 15. And then here we multiply square root of 15 by 15. And then we divide it by 15. So in conclusion, we found out that CB equals to 5 plus square root of 15 times square root of 15 over square root of 15. So CB equals to 5. In the numerator we have square root of 15 times square root of 15 is 15 over square root of 15. So CB equals to 5 plus 15 is 20 over square root of 15. Here we multiply this equation by square root of 15 and then we divide it by square root of 15 in order to eliminate the square root in the denominator. Again, the original expression is 20 over square root of 15, then we multiply it by square root of 15 and then we divide it by square root of 15. We actually multiply it by 1. Therefore we change nothing, therefore it is allowable. So CB equals to 20 times square root of 15. We have the denominator 20 times square root of 15. And the denominator we have square root of 15 times square root of 15 is 15. So in conclusion, we found out that the length of this, but before that, here we divided both the numerator and the denominator of this expression by 5. 20 over 5 is 4, so in total in the numerator we have 4 times square root of 15, and 15 over 5 is 3. So in conclusion, we found out that CB, the length of this line segment called CB, it is equal to either 4 times square root of 15 over 3 units, so in terms of numbers it is equal to 5.164 units. Okay, thank you very much.